So let's start this afternoon with a talk by Chris Fewster from the University of York on something that was alluded to already this morning, but the title is, as you can see, Perspectives on Locally Covariant Quantum Field Theory on Curved Spacetime. Here it seems to be somewhat shorter.
Yes, if it's on the line then. Yes. Thank you very much. It's a great honor to be invited here, so I would like to thank the organizers and also for the organization in general of this wonderful conference. This is a talk which is about work in progress, as you can tell from the title. When I suggested it, I clearly neither knew how many perspectives there would be, nor from what distance, nor even from what angle they would be taken. Had I known then what I know now, the true title would be something like 2.5 perspectives obliquely from the middle distance. Anyway, so we have to see how it goes. This refers to the approach to locally covariant quantum field theory that has already been discussed by a number of speakers, including Rainer and Bob and Stefan and Klaus also. And I want to investigate two perspectives in particular, and the half a perspective is sort of something that emerges from the two taken together. So the question is really, is this categorical framework that has been invoked simply a convenient mathematical package just to say, well, it fits together nicely in a category? Or is it something that's useful, that can be used, and is it in fact something that ought to be used or ought not to be used? So this is, in a sense, the beginning of an investigation, and I think it's one that maybe can go further, but we have to wait and see. The second aspect of the talk is really to investigate in what sense this concept of local covariance actually has physical content. And in particular, the question is whether or not it enforces anything like an idea of doing the same physics in all space-times. In Bob's talk this morning, it's very clear that this is what we all have in mind when we're doing quantum field theory in a curved space-time, or in fact, more generally, any physical theory in fixed background space-times. We want them to be, in some sense, the same theory in different space-times. So there's a slogan that goes with this. The same physics in all space-times is far too long to keep repeating, and as Rainer pointed out to me, it abbreviates rather nicely to Spaß, which is, of course, German for fun. And Rainer is my co-worker on at least some of this work, in which we have had a certain amount of fun, and I would like to share some of that with you today. So, for those of you who do not know, this was a television program which was essentially the German version of Candid Camera, Verstehen Sie Spaß. But it's a real problem, because what do I actually mean when I say I want to do the same physics in all space-times? In some contexts, this is a very easy question to answer. But in an axiomatic framework, I think it's a little harder, and this is where we have to start. So let's start with one simple observation. If a theory represents the same physics in all space-times, then it had better represent the same physics in the same space-time, even when it is perhaps in disguise under a coordinate transformation or diffeomorphism. So that is the motivation for applying or seeking a generally covariant formulation of physical theories. Of course, this goes right back to Einstein. But there's a second thing. I mean, I wouldn't say this is all there is, but there is at least one more thing, which is that if you have two theories that both claim to represent the same physics in all space-times, and they coincide in one particular space-time, then they should be equivalent. Okay, that seems reasonable. Now, an example of this, which is instructive, is the Lagrangian here. This is the Lagrangian of the non-minimally coupled, massless, just to save space, scalar field. Now, there is a constant in here, psi. R there is the Ricci scalar of the metric. And this constant, in a sense, well, it clearly parameterizes a family of Lagrangians, each of which has a set of equations, or one field equation, in which this psi appears. But when the Ricci scalar vanishes, so in Ricci flat spacetimes, then that term just drops out of the field equation altogether. So we have the same equation of motion, and therefore the same classical solutions. However, these should not be regarded as being the same theory, because there is a way of distinguishing them, even in Ricci flat spacetimes, which is to look at the stress-energy tensor. The stress-energy tensor, even in Ricci flat spacetimes, contains terms that depend on psi. So these are not the same theory, even though their solution spaces coincide in this given space-time. But now let me give a slightly different version of this example. I'm changing here the Lagrangian only by virtue of replacing psi times r by a function psi of r. And in particular, I'm going to choose zeta now to be smooth and to vanish in a neighborhood of the origin. Now, in a Ricci flat space-time, of course, we get the same solution space as before. The same equation, same solution space. But now, because zeta vanishes in a neighborhood of the origin, we cannot distinguish this theory using the stress tensor or any other functional derivative of the action from the model in which zeta is identically zero. So this would be an instance of where we have two different theories that coincide in certain space-times, but which clearly are not the same in all space-times. So that might appear to be a problem for the Spaß program, but of course what we typically do is restrict to actions which depend analytically on the metric. That is typically what we do, and there's a good reason, because then we can actually continue from information gained in one space-time. In principle, if you have enough of it, or arbitrarily much of it, but still in this one space-time, you can actually continue to others. So analyticity or quasi-analyticity, or working in some family of functions from which you may distinguish one from another given certain information that can be found in one space-time. Now, of course, normally we don't worry about this because we use taste and good experience and we know what we're doing with classical field theories. But I think there is more of a problem when we come to an axiomatic system setting. So when we are given an algebra of observables or even this functorial description, and we wish to know, is this the same physics in all space-times? There is a question to be answered. Now, I'm actually not going to treat what you might call Vollspaß, the full Spaß problem, but a restricted version, where we only compare theories by when we can embed one as a subtheory of another. So for this talk, the working definition of the same physics in all space-times is something we apply to a class of theories, and we say that it has the Spaß property if no proper subtheory of a theory in the class can fully account for the physics of the larger theory in any single space-time. Okay? So there we have two theories coinciding in one space-time. If the one is a proper subtheory of another, then presumably they do not coincide in all. So that's the working definition. Now I want to start by giving a brief reminder now of what the framework of locally covariant theory is in the form advanced by Brunetti, Friedenhagen and Ferch in 2003. Between them they have too many syllables, so I have to abbreviate them to BFV. That's for the rest of the talk. So here, as has been described this morning, a locally covariant quantum field theory is a functor from a category of space-times to a category of star algebras. The space-times are globally hyperbolic, and they are equipped with an orientation and a time orientation, and there are special embeddings between them that we take as morphisms, namely those that are isometric embeddings preserving the orientation and time orientation, and also so that the image is causally convex, which means that if we have 2 points in this set and a causal curve between them, it must lie completely within the image of this map. So that's the category of space-times. The category of algebras, in a sense, is much more flexible. It's typically taken to be star algebras. Of course, C-star algebras are a very important special case. And the morphisms are required to be unit-preserving star homomorphisms that are injective. Now, to keep this at the categorical level, really we're talking about monic maps in the monic morphisms in the category. So that's the framework, and as has already been explained very nicely, what's happening here is that to every space-time there's an algebra of observables. To every embedding, hyperbolic embedding, there is an embedding of the algebras one in another. So this is embedding the observables on M among the observables on N. And there are coherence conditions which express the fact that if you go from one small space-time to a medium-sized space-time to a big space-time in steps, that's the same as doing the whole thing in one go. Now, in a way, this nicely encapsulates one of the old lessons of algebraic quantum field theory. It's not the algebras, it's the way they're put together. We had this very nicely in Professor Summers' talk yesterday. Category theorists, to some extent, disregard objects. They're interested in morphisms and even higher structures. And in the way, this is a nice reminder to us that in algebraic quantum field theory, it is these embedding morphisms here that are really the object of interest. How the algebras are put together rather than what they actually are. Now, this has been around for 6 years or so, and has had quite a number of successes to its name. It's grown out of the spin and statistics theorem proved by Rudolf Haag, and also the perturbative field theory that we've heard described by Klaus and Bob, and in which Romeo Brunetti and Stefan Hollands have been very essentially involved, of course. I want to emphasize, and I put it in red here, one of the items in the BFE paper is that the formalism naturally gives a notion of a stress-energy tensor. You don't need to get this as a functional derivative of the action or anything like that. It comes out of the basic structures of the theory. We will see how this is important. As John Roberts described, there has been considerable progress in superselection theory in this framework. Quantum energy inequalities that Rainer Ferch mentioned have also been studied in the covariant context and used to calculate things, to calculate numbers. This is an important point. This is not just about formalism. It is a formalism that allows you sometimes even to get numbers in concrete situations. I also mention the Ray-Schlieder results obtained by Co-Sanders, and I am also conscious that I think I have missed a number of other things that have been achieved in the recent past. Now, I want to give a flavor for the tools that make the whole thing work. One is this, the time slice axiom. And we distinguish a special class of embeddings. I'm going to call them Cauchy morphisms, and the condition is that the image should contain a Cauchy surface for the ambient space-time, okay, which I denote here by this red line. This is a Cauchy surface for n. And we say that the theory obeys the time slice axiom if, whenever we have a Cauchy morphism, it is converted by the functor into an isomorphism. So that is the time slice axiom. Now, this has to be put together with a result of Bob Wald and also in Fulling and Narkovich from 1981, which shows how you can connect space-times together. In fact, if you have any two space-times with homeomorphic Cauchy surfaces, then they are linked by a chain of Cauchy morphisms. And you see how I've tried to demonstrate it diagrammatically here. You take the top third or so off, so you can embed that as a Cauchy morphism because there are Cauchy surfaces that loop around like that. you take the bottom third of this space-time and do the same thing. And then you stick them together, and of course that's the bit that you actually have to work on in order to find a space-time so that the bottom third here is isometric to that, and the top third isometric to that, and we can glue them together in the middle and get a globally hyperbolic space-time. This can be done. And it's fairly clear. These two tools together, this deformation argument and the time slice axiom, clearly are going to be very powerful in combination. Now, I mentioned this stress tensor that comes out of the framework, and this is really very clever. What you do is you consider a space-time M, your base space-time, if you like, and a perturbed space-time where I change the metric by adding a symmetric tensor field that's supported in a compact region over here. Otherwise, these manifolds are exactly the same. So I can certainly find a region in the a space-time here, M minus, that can be embedded isometrically in here to either space-time. These are the same function, considered as a map from one manifold to another. Because we're distinguishing them in this category by different metric, we need to distinguish them. Distinguish the morphisms by a label. And I can do this also in the far future of the perturbing metric. And then, if we have the time slice axiom, all of these morphisms get turned into isomorphisms, which means that we don't have to worry about the direction on the arrows. We can run against it if we wish. And so what they do, BFV, is start in the top left-hand corner and run around like that, putting together the morphisms, putting in inverses where they need, to get right round and back from M to itself via the perturbed space-time. This is, of course, an automorphism because it is a product of a composition of isomorphisms. Very nice, but even nicer is the next thing. You can, or they could, they still can, I suppose, functionally differentiate this automorphism with respect to the perturbation. And this then has the interpretation of giving, after correction by factors, the commutator with a stress tensor. How do we know it's a stress tensor? In BFV, they showed that it is symmetric, that's not surprising, conserved, which is important. And furthermore, in a particular model, namely the free scalar field, they check that the standard formula for the stress tensor does indeed agree with this functional derivative here. So this is a really important thing. This, remember, starts in general without any action, but nonetheless you can extract a stress energy tensor, at least in the sense of a derivation. Okay, so the next question is, well, can you then extend that to a field? But let's put that to one side. Now, one of my original motivations was to ask whether we can fruitfully study quantum field theory at the functorial level, to which end I'm going to put all of these theories together and make another category out of them. So this is the category in which I'm calling it LCT for locally covariant theories, in which the objects are functors from the manifolds to the algebras, or space-times to the algebras, and the morphisms are natural transformations between them. This is, to category theorists, simply a functor category. And in the spirit of Spaß, I'm abbreviating that as fun. Right. Now, a natural transformation between these theories is simply this. To every space-time, there has to be a morphism between the two theories, what they say about this space-time, and then a commuting diagram of the sort we saw in Rainer's talk in the context of quantum fields. And this is simply the statement that the components of the natural transformation intertwine the actions of the two functors. Now, that's the mathematics. Physically, what this says is that zeta embeds A as a subtheory of B. And in the special case, where every component is an isomorphism, we say that zeta is an equivalence of the two theories. Now, examples of this, a simple one is that if I have any theory A and I choose my category alg so that it has a tensor product on it, I don't care particularly what, but part of the specification of the category is a tensor product, then I can define a new functor, a to the tensor power of k, simply by tensoring together k copies of the underlying algebra. So this is certainly something I can do, and on the morphisms, which is the important thing, I simply tensor together the k copies of the map. That is a functor, is easily checked, and of course, unsurprisingly, if I have k copies and L copies, and L is bigger than k, I can put k copies into L copies. And I can do this with a natural transformation. The component, so in space-time M, all it does is tensor in an appropriate number of extra factors of the identity on the end of whatever observable we're moving across. This, again, it's very easy to check, is a natural transformation, or family, a whole family of natural transformations. And here, this is one of the places where the unit-preserving nature of the functor is, of the morphisms, is very important. There's also a sort of groupoid property, but all it means is that if you go from k copies to L copies to M copies, these natural transformations stick together in exactly the way you would expect. So there is a simple example of a system where we can have subtheories, and they are embedded by natural transformations. An example where you cannot is if you have two theories which in Minkowski space reduce to Weitmann theories and which have their distinct mass spectra. These cannot be equivalent. In fact, and this is an argument given at least in a special case in BFV. Now, this is what I have proposed to study, but it raises some immediate questions. So firstly, and this might stop us doing it, is there any operational content to this? And this, I think, is close to the concerns of Steve Summers' talk. So, we only ever have access, experimentally, to one space-time, namely this one. And actually, not even complete access to that, but for many purposes, we often assume that we do. But we would have a real problem if you could have two theories that could not be distinguished, two morphisms between theories that could not be distinguished on the basis of their action in one space-time, because otherwise how would we know which transformation we're talking about? The other question is, have I just opened a very large mathematical can of worms, and there may be many, uncountably many, and you worry about large sets and models of set theory and who knows what. Could this actually just be so large as to be ridiculous and no use whatsoever? And also the concrete question, can you compute what these Hom sets are? What are the morphisms from one theory to another in concrete cases? So I want to show how you can answer these, and in fact the first one is quite easy. Very simple arguments give you three nice little lemmas. Firstly, if we have two of these morphisms that agree in some space-time M, then they also agree in any space-time that embeds in M. So the proof of that is a one-liner. I use the natural property in space-time L to pop that one through. The L turns to an M, the B turns to an A, but in space-time M I know this is the zeta prime M, and then I do the same in reverse to get my zeta L back. But B of psi is monic, and what that means is I can cancel it from the left. So I do that, I get rid of those, and then I have that zeta L is zeta L prime. Now the second one, so that's an inheritance property coming down. We also need to go up, or at least across, and that is given by the following property. If I have a Cauchy morphism between two theories and the theory obeys time slice, then again the equality transfers. And this time the argument is very similar. I use the natural property again to get from zeta of n to zeta of m. I turn that into zeta m prime and go back using the natural. This time I need to cancel from the right. And I can do that precisely because this is A of phi is an isomorphism. So that's why I can cancel it this time. That's why I need time slice. And finally, if I put these two together and I invoke the space-time deformation argument, then it's immediate that if I have two space-times with homeomorphic Cauchy surfaces, then again we have equality of the zetas. And the proof is simply find space-time deformation and Cauchy morphisms. And you'll see that I'm running one way or another through these morphisms. It doesn't matter because I have results that allow me to do it either way around. So that's quite, that gives us a little toolkit. I now need to do something slightly more. John Roberts in his talk mentioned diamond spacetimes that are very important in superselection theory. They are domains of determinacies of open balls that lie in Cauchy surfaces. They are very convenient for many purposes. If I now take a diamond of, let's go back for a moment, take a diamond of this space-time, I can of course regard it as a space-time in its own right with a very obvious embedding. And then I can use this inheritance property and deduce that zeta and zeta prime agree on the diamond now freely floating as a space-time in its own right. But all diamonds have homeomorphic Cauchy surfaces. They are all homeomorphic to a 3-ball. So now we know immediately that the zeta and zeta prime agree on every diamond of every space-time. Okay, so now we're actually being able to move around quite freely in this category. And what I need to glue it together again is some sort of additivity property. So if I can generate the algebra of m tilde by using the subalgebras of A m tilde that come by regarding these diamonds as freely floating and then using the functor to embed the resulting algebra in A of m tilde, if from those I can generate the whole thing, I will call that additivity. And then it's not a great surprise perhaps to see that we now have gone from equality in one space-time to equality in all space-times. So this is this operational aspect. It actually, I think, now does make good sense to consider morphisms in this category because we can tell them apart on the basis of what happens in one space-time, the only one we have at hand. Now, there's another useful result here that comes from the relative Cauchy evolution, which is that if I take the relative Cauchy evolution of theory A and the relative Cauchy evolution of theory B, they are nicely intertwined by the action of the natural transformation for all perturbations of the space-time preserving global hyperbolicity. I'm not going to show very many diagrams, but just to give you an idea, here it is. These are the diamonds are what you use when you consider the relative Cauchy evolution in theory A and in theory B. Now we have a natural transformation which puts in edges like that, these verticals and horizontals. Every one of the trapezia we have around the outside commutes by virtue of the natural nature of zeta. And moreover, the time slice property means that all of the slanted morphisms are isomorphisms. And that means we can run around the inside and then out to the edge, or we can go out to the edge and then run around. Okay? And this is just to do with the way the natural transformations work. And the fact that in any of those trapezia, I can reverse the direction of both parallel lines, given that they're isomorphisms, and the diagram still commutes. So this is a very simple, but nonetheless rather useful argument, because it shows how tightly the structure of these theories, considered as a category, is bound to the idea of the relative Cauchy evolution. So what we've got so far is a little theorem that says that if A and B obey the time slice property and A is additive, we don't need that for B for some reason, then the morphisms between A and B are uniquely determined by components in one space-time, any space-time. It doesn't have to be Minkowski space, it can be any space-time. There is this nice intertwining result for relative Cauchy evolution, and if I functionally differentiate, this translates to the following statement, that I can take commutators with the stress tensor of theory A and pop across to theory B using the natural, or I can take my observable, pop that across using the natural transformation, and take commutators with the stress tensor in theory B, and it gives me the same answer. Now, this was very elementary, but it allows the beginning of calculation in concrete cases. And I'm going to report the result now. I'm not going to go through the proof. But if, for example, we were to take the real Klein-Gordon equation, real Klein-Gordon field in the version Rainer gave us this morning of mass m, and I tensor together n copies of this, like that, then I can ask in particular, what are the endomorphisms of this theory? Those are the natural transformations from the theory to itself, the ways in which I can embed this theory as a sub-theory of itself. Well, can I do that or not? It turns out that I can only do that using automorphisms. There is no proper sub-theory of the theory of n scalar fields that is equivalent to the theory of n scalar fields. That's actually quite reassuring, right? Because it means that there is a difference between one field and two fields, which otherwise might cause you worries late in the night. Now, we can also compute what these automorphisms are. This is a group. As with any functor, the automorphisms form a group. And it's ON, if you've got a massive field. The only thing you can do, phi here is standing for the sort of vector of n scalar fields. F is standing for a vector of test functions. The only thing I can do is choose a rotation and rotate the fields around. In the case where there is only one field, what this amounts to, O1 being Z2, what this amounts to is simply the freedom to switch the field phi for minus phi. That's all there is. That's the only thing one can do in this natural transformation language. So this is not such a great big can of worms. It can actually be quite small, in fact very small, almost small as you like. Now that's the massive case. In the massless case, we also have the freedom to rotate around these fields, but there's a little bit more. There's a semi-direct product with Rn, and what that amounts to is the freedom to add in a multiple of the identity. And I'm not going to particularly, the precise formula is given for the experts. This is the advanced minus retarded function. Alpha is a constant. It's regarded here as a constant function on the space-time. Effectively, this is related to the fact that the classical theory has solutions which are constant everywhere. Okay? And you can check that this is an automorphism of the theory. So the interpretation that I draw from this is that this automorphism group is actually quite interesting, not just something to calculate. This is, in fact, the global rigid gauge group of the theory. This is all transformations of the theory to itself, and it turns out to be exactly what you would want as the global gauge group of the functor assigning these field algebras. Which also means that if there are no gauge transformations, if this group is trivial, we could legitimately say that what we have is a theory where the algebras are all algebras of observables. Okay, and there's all fixed out there. Furthermore, the linear fields of the theory will now begin to appear in multiplets corresponding to group representations of this automorphism group. And that suggests the beginning of a program where you could actually classify all possible fields associated with the theory that we have. More ambitiously, I think that I would be very interested to see how superselection theory fits into this framework from the top down. Okay, I'm starting at the functorial level. In Giuseppe Rozzi's work, he started space-time by space-time and showed how in large class of space-times you could apply superselection theory. And with Romeo Brunetti, they then extended this using locally covariant techniques, but they find a group that actually changes. The sectors change from space-time to space-time, and that's to do with topological features that are specific to certain space-times. So I wonder whether or not what one should aim at is this global gauge group. If you were to do the whole loop of saying start with a field algebra, take the associated observables, try to reconstruct from that the theory with the gauge group, again, an algebra of fields with a gauge group, well, it should be this original automorphism group that you are aiming for. And then the additional structures that Brunetti and Ruzzi find have to be understood as specific features that relate to specific topologies in that the various spacetimes might have. So I view this as complementary, and it's certainly a long way ahead of what I could actually claim to do at the moment. Now, I want to move to the second perspective and get back to Spaß. So let's have some fun with some functors through gritted teeth. And I'm now going to do something which is a little bit strange. This is, by the way, almost to be understood as, well, actually it is to be understood as a joke. I'm going to take a functor from the spacetimes to the category of locally covariant theories. This seems to be a strange thing to do. So if I write it out in full, it's in a functor category from the functors, from the manifolds, to the functors, from the manifolds, to the algebras. Okay, that's what it is. What is it? It is a locally covariant choice of locally covariant theory. Every time you give me a space-time, I give you a fully fledged theory in all space-times. Every time you tell me about an embedding of one space-time in another, I give you a sub-theory embedding of the theory assigned to space-time M as a sub-theory of the space-time in N. Now, this is not at all what you want. We are interested in theories that are locally covariant, functors from the manifolds to the algebras. But there is an elementary construction to go from phi to what I call a diagonal theory, a functor that is an actual object of this LCT category. This is how you do it. For every space-time and every hyperbolic embedding of this in some other one, I just define phi delta of M to be what the theory assigned to space-time M has to say about space-time M. Of course, the really interesting thing, as ever, is the morphisms. This formula doesn't look so obvious, but when you look at the natural square, it jolly well is obvious, because I need to go from phi mm to phi nn. How else would I do it except straight down the diagonal of the natural square? And that is reflected in the formula given there. I'm not going to prove that this is a functor. You then need to just build a 3x3 diagram and check that the whole diagonal is equivalent to just doing it in 2 stages. It's a naturality again. But phi delta is a functor, and therefore, according to the rules of the game, it is a theory we can take sort of seriously. But this was a choice of theory in every space-time. There is no guarantee that this is the same theory in each space-time anymore, and indeed it need not be. Here's a construction. I'm going to write sigma of M for the Cauchy surface of M modulo homeomorphisms. And then if I choose any topological invariant valued in the natural numbers, it's a topological invariant of the Cauchy surface, which assigns the value 1 to every space-time with non-compact Cauchy surface, then I can build a theory like this. I just take, for each space-time M, mu of M copies of whatever theory it was I had in the first place. So this, again, could be quite general. And for the morphisms between the theories, I just assign this eta. Remember I had, which went between mu of M copies of the theory to mu of N copies of the theory. And my claim is that this is a functor. The key point is really only to make sure that it's well defined, because remember I obviously can only do this embedding if mu of M is always less than or equal to mu of N. And geometrically, this is actually the case, because if I have a compact Cauchy surface and an embedding of m in n, then actually one can prove that the Cauchy surfaces are homeomorphic. So mu of m is equal to mu of n. And therefore, it follows that I always have this sort of order property whenever m goes into n, because either m has non-compact spatial section, in which case this is 1 and I don't really care what that is, or m has compact spatial section, in which case these two are equal. And then the fact that this is a functor follows immediately from that groupoid property that I mentioned that the etas have. So here's the picture. Take the simplest of all examples, of all non-trivial examples. Mu of m might be 1 if the Cauchy surface is non-compact and 2 otherwise, which means that on a little diamond I have assigned 1 copy of the algebra that I would normally expect, but on a space-time with maybe toroidal spatial section, I have 2 copies of the algebra assigned, and this is locally covariant. It is a functor, right? So this is within the rules of the game, and we need to worry about what we have just done. Moreover, there are natural embeddings, both of the theory of 1 copy of A into phi delta into 2 copies of it. And as you can see, in some space-times, these are going to be isomorphisms, not at the same time, but not in all. So the Spaß property fails. In LCT, there is no Spaß. Or not enough, anyway. Right. Let's have a think about the properties. This is very strange, because what we've got here is a theory, locally covariant theory, that is more than 1 copy of the field, but less than 2. Right? 1 and a bit. It is a functor. It also is not so badly behaved. If your underlying theory has time slice and causality, so commutation at space-like separation, then so does phi delta. That's not bad. The other thing is that you should be worrying about, how do I know that actually that and that are not equivalent? Well, I already told you that, because, for example, for the scalar field, they'd have different automorphism groups, right? Z2 versus O2. So I know that they cannot be the same, at least in obvious examples. Now, an interesting property occurs when I look at these diamonds again. And I ask, this, by the way, M restricted to O is just my notation for regard O as a space-time in its own right, inheriting all of the causal structure from M. When I do that, because the diamonds all have non-compact spatial section, they all get mapped to 1 copy in themselves, which means that our theory phi delta is not additive. It also means that the local algebras, these ones, are insensitive to the ambient algebra in which they are put, and then might make you think, it's all right, this is just 1 copy of the theory, but in disguise. Okay, so maybe it's not so very exciting. Well, actually there is something that can distinguish what the ambient degrees of freedom are, and it's the stress tensor and the relative Cauchy evolution. Because we have this intertwining rule, remember, when I go from one theory to another. And if I compute it for a diagonal theory, I find that the relative Cauchy evolution factorizes into 2 things. This is the bit you might expect. Remember, this theory was concocted by sticking together different theories in different space-times, and here is the relative Cauchy evolution of the theory phi of m in space-time m. So that's what you might expect. This bit is a little bit less expected. It is actually another relative Cauchy evolution taking place in a different category, namely the category LCT. This is the evolution of this functor that assigns locally covariant theories by space-time perturbations. Now, actually, I've not yet constructed any examples where that's anything other than trivial. So let's drop this factor for the moment and at least study those models where it is trivial. Then we get the nice fact that the stress tensor of the diagonal theory in space-time M is exactly what you're expecting. It is the stress tensor of the theory assigned to that space-time. In other words, it is the stress tensor of the ambient degrees of freedom. So in the example I gave, on the diamond, I have the stress tensor for one copy, and on this space-time with toroidal spatial section, I have the stress tensor for two. So this relative Cauchy evolution does what the local algebras do not, and actually picks out the ambient degrees of freedom. And that, of course, is how you can begin to put a lid on these things. It suggests we need this class of examples suggests we need a new principle, and this slide here is the starting point, because we can actually use now the relative Cauchy evolution to define some intrinsic local algebras based on the stress tensor, or the relative Cauchy evolution. I just take in A of m all those elements that are invariant under the relative Cauchy evolution. This is based on some compact set K. They have to be invariant under the relative Cauchy evolution in the causal complement. Now this goes back to what Bob was saying about fields should not depend on the space-time away from that point. Well, actually that isn't implemented in local covariance by itself. It's an additional requirement. So this gives us an intrinsic definition of some algebras of compact sets. To get algebras of open sets, which is what we normally like to play with, I put some of these together. I take all compact subsets of our region O, and I generate using these algebras. I also don't let the K get too big. So I'm going to insist that they have diamond neighborhoods in this generation. And then a definition. The theory is going to be what I would call strongly local if the intrinsic algebra of the open set agrees with the extrinsic algebra of the local set, which is the one assigned by BFV, namely treat this region as freely floating space. If it's globally hyperbolic, treat it as freely floating and consider the subalgebra of A of m you get from the functor. So you are not guaranteed that these should agree. This is the example, but we can adopt as a new axiom this strong locality property that requires that they do. Now, there are some consequences of making this. The first is that the theory is guaranteed to be additive. That comes out of the technical way that we've generated the algebras of open regions from those of compact regions. But we also have the Spaß property. You can prove, I'm not going to do it here, but that if you have two strongly local theories and a natural between them, and in one space-time we have the component is an isomorphism, then in fact this is a natural equivalence. And this is Spaß in the restricted sense that I'm talking about today. We can infer two theories are equivalent on all space-times based on observations made in this one, if we restrict ourselves to this category of strongly local covariant theories. So this is a category that does actually have the Spaß property. Now, it's also an interesting question to see what happens when we apply the framework to the diagonal theories. Okay? So what happens, for example, if we were to consider a diagonal theory which has this nuisance factor trivial, and such that it and all of the phi m's that went into building it up are strongly local. And then actually there's not that much freedom left. All of those component theories turn out to be naturally isomorphic. So you can't use different theories, they are all equivalent. Moreover, this diagonal theory is then itself equivalent to another theory where the morphisms are related to those of fix some m0, Minkowski, de Sitter, whichever, and then composed with a component of a natural which is actually a functor eta is a functor from the space-times into the automorphism group, in other words, the gauge group of the theory assigned to space-time m0. So this is a little bit of a twisting, perhaps, of the theory. It says that there is a little bit of freedom left when you consider this theory, and you can sort of twist it round as you hop around the algebra. Maybe, of course, I haven't shown you that there are any functors in here other than constant ones. And that, of course, raises many interesting questions of a cohomological nature. And what we really need to do is to adopt the net cohomology that Roberts and Ruzzi use. We need to adapt that. Instead of looking at posets of open sets in given space-time, we want to do the same thing, but just hopping around in the category. So this framework should generalize. Well, I mean, I know from talking to the experts, this generalizes very easily. And then you're left with a cohomological problem of computing cohomology classes of this category and with values in the gauge group. What you then achieve will be in some way not entirely clear to me right now to the net bundles that Robertson, Ruzzi and Verzelli have constructed or described in their work. Now, in a particularly simple case, if we restrict to the case where the gauge group is trivial, and we really are working with theories of observables, then, of course, this automorphism group is trivial. And that's good, because it means that these diagonal theories really are all equivalent to one of them in fixed space-time. So that really puts the lid on all of these possibilities. Okay? Strong locality is sufficient to reduce it from this menagerie of peculiar examples to what you would like to have had, and in fact what I don't think Rainer or I were quite expecting, to get this additional little twist, but it is possibly there depending on the solution to the cohomological problem that I mentioned. Now, I need, of course, to give you an example to convince you that any of this works. Take the Klein-Gordon field, as ever. There are not that many other things we could take, frankly. And let's take a positive mass to start with. This is strongly local. When you look at this algebra, we're looking for remember, for the elements of the field algebra that are invariant under relative Cauchy evolution in the causal complement of K. And those turn out to be exactly the subalgebra generated by fields smeared with functions supported in K. Now K is compact, so this support can stretch right out to the edge. Okay? And this is actually the reason, the original reason for this step from the realizing firstly that these algebras are probably more properly associated to compact sets than to open sets, because we started with an open set and found that the support stretched to the boundary. So really it's about the closure. To get what we would normally have for the local algebra, we need to just stretch things out by allowing ourselves to stick these local algebras together, the ones on the compact sets. So that one was strongly local, but life is never entirely simple, and well, after listening to this talk you might think life is hardly ever simple, in fact. But if you take the massless field and on a space-time with compact Cauchy surface, it doesn't work. There is a mismatch between the intrinsic algebras and the extrinsic algebras. The reason is there's another generator. And this generator is, in a sense, pure gauge. And it comes from the fact that the massless field always has a constant solution. And in non-compact space-time, we actually throw it out, because we only consider solutions that have compact support on Cauchy surfaces. But here it is in the compact Cauchy surface case. Right, so that leaves an interesting question. Should I change my definition or throw away the theory? Now, I actually am a little bit down on the massless free field, apart from messing up my nice idea, because there are other things, other problems that crop up from time to time that really annoy you. And one of those is that if you have a static space-time of whatever dimension, and you look for a static ground state, the space-time, if the spatial section is compact, there is no static ground state because of this zero mode. So this is actually related to other pathologies. And at the moment, although I am open to changing this view, I would like to say that we should live with the fact that, well, strong locality is, as it were, the right definition or the foundation of the right definition, and we live with the fact that the massless free field does not obey it, but it's a signal for something else going wrong. Now, part of the reason for going down this route is discussions I've been having this week with co-Sanders, where we've been looking at the Dirac equation. And you can compute the local algebras, and in the massive case, again, it's strongly local, as you would expect. And again, as you would expect, there are some problems in the massless case. And they come from the existence of covariantly constant spinors. But covariantly constant spinors only exist in rather special space-times. In particular, they have to have vanishing Ricci scalar. So this is destroyed at the moment you start perturbing your space-time in relative Cauchy evolution. So in that instance, it seems that it is likely that this is a strongly local theory even when the mass is zero. And for that reason, I tend to think that this is a pathology of the massless scalar field, the existence of a gauge mode that is stable. As you perturb the space-time, it doesn't know anything about it. It carries no energy momentum density. It's only there in these particular space-times. That is a pathology, I think. So, I'm nearly at the end of the time. To summarize and outlook, local covariance by itself does not enforce Spaß, but it does, and this is a very important thing, I think, open new ways of analyzing quantum field theory. We have seen how the global gauge group appears in a very natural way as the automorphism group of the functor that we start with, and that it does carry the interpretation of a global gauge group. There are these joke theories, the diagonal ones, which even if you don't like strong locality, you will if you don't like strong locality, you will have to deal with somehow or other. Either by pursuing a path like Bob and Stefan and saying, I know what the list of fields is from the start, or by some other means, or living with the fact that these strange things might be there. Maybe that's not a problem for you. Strong locality, however, does get rid of them nicely. And what I want to emphasize above all is the key role in all of this analysis of the relative Cauchy evolution and the stress tensor that it engenders through functional differentiation. Looking ahead somewhat, if we pursue this analysis at the functorial level, could it be that we really can do quantum field theory in curved spacetimes without the spacetimes? In other words, at this higher level, dipping down for examples or calculations, but formulating many of the concepts at that higher level and seeing how they go. Maybe that might be helpful, maybe it won't. It has to be justified by progress. Interesting possibility of doing superselection theory at that level, in which you would need the cohomology of the space-times. And a final thought, it's been traditionally regarded that quantum field theory in a curved space-time is hard or awkward or difficult because there are no global symmetries of the sort we have available to us in Minkowski space. That is to the traditional view. But I'm beginning to wonder if perhaps quantum field theory in Minkowski space is hard because it does not have the relative Cauchy evolution and stress tensor that you have in a locally covariant, or even better, strongly locally covariant field theory. And that, again, building on that, perhaps any theory that does have a sufficiently nice stress tensor is already a theory possibly defined in all space-times with the same physics. Thank you.
Thank you very much. That is very clear, Bob. Are there questions, or have they all been answered already? Or maybe asked already? Yes, please.
The last example that you mentioned, muscles,
Yeah.
looks like as this intrinsic algebra is some sort of universal. This addition of these looks like central elements.
Yes.
Always.
Yes.
Try to look.
Yes. It could.
Do you have any
No. But in a sense, there is. I would pick up on the idea of universality, maybe not quite in the way that you mean. In your paper, the BFV paper, the local net comes for free, or at least a local net comes for free. And I think one of the interpretations of strong locality is that this supplies a job for it to do. Instead of being one of the possible things, that would be the, as it were, universally preferred way through which all other local nets would have to sit inside as subnets. So there is an aspect of universality. Maybe that's slightly different from what you were thinking about. Yeah.
Is there a cosmological obstruction to the difference between the possible difference between internal and external?
Almost certainly so, because of the need to get these functors from the locally covariant theories, from the space-times to the locally covariant theories. And for example, the very first thing that would go wrong with the construction I gave of this slightly twisted one, where you need a functor into the gauge group, is that maybe you can put the same space-time into a bigger one in two ways. And so you have to have agreement on all of those different ways of doing it. And then if you sort of try to trivialize this whole thing, you get a chain of other conditions which are indeed cohomological in nature. So yeah, I think that cohomology is definitely, in its various guises, is probably the way to investigate this. Yeah.
Has anybody considered the adjoint factors? I mean,
Yes.
from algebras to manifolds, obviously adjoint to those.
Well, I mean, that is a very interesting thought, because of course there's a long-running, very long-running story, question about whether you can reconstruct the space-time from the algebra of observables. And that is a very nice suggestion, but as far as I'm aware, no one has contemplated it. I think, as I said, this was work in progress, and a little bit of a race to the finishing line. There are some hints of adjointness around the place, which I am going to follow up, but that I hadn't thought of. I think it's a very nice thought.
What is the name of the category of supermanifolds?
Oh, spam. Yes.
Okay. It seems there are no more urgent questions, so thank you again.
Thank you.